Hello, my name is Jason Bondarchuk, and here is my presentation for Project 4. I will now show one sweep of the value iteration algorithm on the L track. First, I have a recursive algorithm that gets all possible states. Here is one instance of the value function. For all states in S, calculate the Q value of the state and all possible actions, and update the table with the maximum. This side contains the value updates for one sweep. Next, I will demonstrate the Q value updates for the Q learning algorithm on the L track. Our Q learning condition is a purely greedy strategy. This is the equation to update the Q value in the Q table. Here are the Q value updates for one episode. Next, I will show you the Q value updates for the SARSA algorithm. SARSA employs an on-policy strategy, which is epsilon greedy. We calculate the following Q value here. Here are Q values updated for the SARSA algorithm. Next, I will demonstrate the epsilon greedy strategy using the SARSA algorithm. The epsilon greedy strategy is as follows. We first have the policy choice. Using a random number, we verify against epsilon. Here is a case where we choose the greedy strategy. We iterate over all states and set the greedy state. Finally, we return this value according to the maximum Q table value of the possible states. Here is a case of the random strategy. It simply returns one of the states at random. The following is path generation at the end of the Q learning algorithm. According to this path, A represents any place the agent has been, F represents a non-deterministic failure to accelerate, and R represents a random choice. I will now demonstrate the path at the end of learning for the SARSA algorithm. Again, F represents a failure to accelerate, R is a random choice, and A is the agent. The following is a path generated at the end of learning for the value iteration algorithm. Here we can see where it failed, where the agent was, but there's no random choice. It's a purely greedy approach. I will now demonstrate the clipping algorithm that detects collisions. First, all points between the start and end of a time point are recorded. Here's the algorithm for collecting all of the points traveled between the start point and the end point. These algorithms walk the points and add them to a list. This occurs from start to finish. We then iterate from start to finish on the traveled points and detect if any of these points is a crash. Crashes are detected if it's out of bounds or a wall. I will now demonstrate the restart to nearest crash policy. Here the agent had traveled 3 points. We detected a crash at index 1. We call the handle crash function, which takes in the last valid point, the last point on the track. Since our crash policy is reset to nearest, we set the position at the current point. We also zero the acceleration and velocity. I will now demonstrate the reset to start crash policy. Here we traveled 3 and crashed on index 2. It zeroes acceleration and velocity and then resets to the start position, which was selected to be 1-8.